Okay. The exam, I think, is going to cover from, let's see, we ended the last one with what, aromatics? And we didn't have any ketones or aldehydes. So it'll be chapter 22, ketones and aldehydes, up through what we did yesterday. So that's going to be the material. There's a lot of overlap within the chapters, aldehydes, ketones, etc. So it'll be same format as in previous exams and as we've done. There'll be a couple mechanisms, writing products, giving reagents, and then a catch-all if there is a catch-all. You won't have to synthesize anything from benzene. We've done that, so it probably might just be the rest reactions and reactants and products. So the last couple of exams will have the last section that we have not covered yet. So if you see anything that looks completely like we haven't covered it, that's probably the case. But there's we still have chapter 26 to end next week. Okay. So questions?
Can you go over those problems where you have to change the stereochemistry? I think it's the Hoffman and Cope.
The Hoffman and the Cope. So if I gave you a Hoffman and Cope problem, like, and you'll see this on the older exams, I might give you something that looks like this, where I would say, okay, here's my NH2, there's a CH3, there's an H, here's a CH3, here's maybe an ethyl group, and here's a hydrogen. So I would say we're going to react 3 equivalents of CH3I under basic conditions, and then we're going to do the elimination that way. So what I would ask is I would ask you to write, or if I'm going to make grading more efficiently, and I wouldn't count on this, but I could give you all the possible products and say circle which one's the major product and which one's the next one. But don't count on that, because that's probably not going to happen. So if I said, what is the major product of this reaction? First of all, what is this? Is this Hoffman or is it Cope? And does that matter? It's going to matter for the second product, the stereochemistry of the second product. But what is it? Hoffman or Cope?
Hoffman.
It's Hoffman, because I'm basically going to alkylate this nitrogen group to make the ammonium. And I'm alkylating it 3 times. That's Hoffman. If I just alkylate it twice and use something like a peroxy acid, that's Cope. Do you have to know those names? Not really, but you need to know which is going to be antiperiplanar and which one's going to be planar. So in this case, my final product is going to look like this. Once I do my alkylation, my nitrogen is going to have 3 CH3 groups with the positive charge. Everything else stays the same. So let's write the major product of this reaction. How am I going to do that? Well, my hint would be, I guess I'll ask all rhetorical questions today, which means I will answer them. how am I going to figure out the major product? How am I going to figure out the second major product? Since this is elimination, here's my alpha carbon, here's my beta carbon, here's my other beta carbon, and then I'm going to look at the beta hydrogens. So if I call this beta hydrogen A and this beta hydrogen B, which hydrogen do I lose to make the major product? A or B? Melanie? B? Do we all agree with that? Why B? It has the most hydrogens. Keep going. Keep going. Keep going. Right. So what do Hoffman and Cope give you? The least substituted product is the major product. So which one of these beta hydrogens, when you lose it, gives you the least substituted product? B. So we would write the product then of losing beta hydrogen B. Nothing happens on the left side. Everything stays the same. Except now I'm going to lose the beta hydrogen B, and I'm going to lose the ammonium. So that means I'm going to end up with that. So that's going to be my major product. The major product of Hoffman or Cope is the least substituted double bond. So is there stereochemistry with that? No. Because normally we're losing a hydrogen off of CH3. So this double bond is not, it's neither cis nor trans nor E nor Z. Okay. So that's going to be the major product. So the major product is pretty straightforward to write. But then I'm going to ask you to write the second major product. So in the second major product, I'm going to have to now lose beta hydrogen A. And so I need to know, is this Hoffman or Cope, simply from the fact is it anti-periplanar or is it periplanar? And Hoffman, with the ammonium salt that's being lost, or with the ammonium group, is always anti-periplanar. So this is Hoffman. I think there's just one F. And it's going to be anti-periplanar. So now what I've got to do is now I've got to put that beta hydrogen A into an anti-periplanar geometry. So that means I've got to basically, the hydrogen I've already put in an anti-periplanar geometry. And so now what I need to do is now I need to rotate this group, the right-handed carbon, rotate around so that I put the NCH3 plus group anti-periplanar to that hydrogen. So that means I'm going to rotate the nitrogen group down, rotate the hydrogen up to the methyl, rotate the methyl into where the CH, or where the nitrogen group was. Okay, so I'm going to rotate, and so that's what I'm going to get if I rotate that around. And so now when we heat this system, I lose my hydrogen, I lose my nitrogen. The groups that are bold The groups that are on the bold wedges will be cis. The groups that are on the dashed wedges will be cis. So in this case, on the left-hand side, I'm going to have an ethyl and a methyl. And then cis to the ethyl group is the hydrogen, and cis to the methyl group is the other methyl group. So this would be the second major product. And when I introduced this before, I said, well, I probably used the exact same molecule and said, are the methyl groups going to be cis or the methyl groups going to be trans? I mean, understand, I don't have to vary this molecule because all I have to do is put them in different positions and you would get a different answer. Now, is it 50-50? Yes. Could you guess? Sure. What's the worst that's going to happen? You'll probably get half credit. But you're not striving for half credit. You're striving for full credit. Right? So this is the more difficult part for Hoffman or Cope, is to put the geometry, put the molecule into the sawhorse geometry that it needs to go. You could put it into a Newman projection if you wanted to. So you could look at this molecule up here. We could look at that molecule, and I got to remember exactly how to write it. Let's see, what goes here? Methyl, ethyl, ethyl, and then the methyl, and then over here is the nitrogen, and then what, the hydrogen, and then the hydrogen. So you could say, I'm going to come over here, and I'm going to write the Newman projection of that. The Newman projection would look like this. The front carbon would have the hydrogen on top, the ethyl group to the left, the methyl group to the right. Over here, the nitrogen with the CH3s. The ammonium would be there. The hydrogen would be down, and the CH3 would be here. So you could put this into the Newman projection. Say I need to rotate the back carbon 120 degrees, so that I need to put, that is my beta hydrogen I want to lose, then my ethyl group, then my methyl group, now my nitrogen is going to be on the bottom, the hydrogen is going to be here, the methyl group is going to be there, so that now when I lose those two groups, the methyls are cis, and the ethyl and the hydrogen are cis. So you can do it either way. Again, whatever works for you. So that's Hoffman. Hoffman is anti-periplanar. But again, the first product of forming the CH3, that's the major product regardless of whether it's Hoffman or Cope. Because you're always going to form the least substituted double bond. So you don't have to worry about the stereochemistry there. It's the second product you have to worry about the stereochemistry. Do you want to see the Cope? Okay, then let me just change this over to a Cope then. So if I changed it over to a Cope, I would start with the NH2, but then what I would say is I'm going to react 2 methyl iodides under basic conditions. And then secondly, so I'd probably say I'm going to do that first, then secondly, I'm going to react this with a peroxy acid. So that the final product, the nitrogen has been alkylated twice. So it's got 2 methyl groups on it, and the oxidation of the peroxy acid then produces the amine oxide. Except that should be so the same idea of determining the major product. This is going to be my leaving group, my alpha. There's my beta carbon. Here's my other beta carbon. Which beta carbon is going to be least substituted? The beta carbon on the right side. So the major product of this reaction is going to have the double bond to the major product is going to look exactly like the other one did. I'm going to lose my hydrogen off of my CH3, the beta carbon that's a CH3. So that's going to be the major product. And then as far as the stereochemistry on the second major product, or the second most major product, I'm just going to rewrite what was here. So I'm starting with that. I'm starting with that geometry, which is exactly how I left it off. But now I've got to rotate the nitrogen to make it planar to this beta hydrogen. So I basically have to rotate the right-hand carbon, so I end up with this. Again, nothing changed on the left carbon. But now rotating the nitrogen, which was towards you, I'm going to rotate that back 30 degrees, or actually back 60 degrees. That means that this hydrogen, if I rotate this back a little bit, that's going to put it in the plane. This hydrogen that was in the plane is now going to go ahead and come forward, and the CH3 is still going to be pointed in the back. And so now the amine can come in, grab the hydrogen, the pair of electrons goes there, pair of electrons goes to the nitrogen. Again, groups that are dashed are going to be next to each other. Groups that are bold are also going to be cis to each other. So because this was the same molecule that I gave you, Now the methyl groups end up trans in the second major product. Now, will I give you the same product or the same starting material for each of those two reactions? I don't know. So don't assume that unless they are identically the same, don't assume that they are. Because you could say, oh, because this was Hoffman, it's this stereochemistry. Okay, this one's Cope, that's going to be the other stereochemistry. That's only if the two molecules are the same. If I give you two different molecules to do this with, they're individual. Could I do that? Yes. Will I do that? Who knows? Depend when I write the exam. So it's the second major product that has the stereochemistry. Is that good with that?
So is that on the left side, so where the methyl group was, would you want to rotate the left side then?
If this was the original molecule and the hydrogen was here, I would actually have to rotate both the right and the left because I need to put it in this conformation. I need to put it in the conformation where these groups, where those three groups are planar. So I'd have to rotate the methyl group up into the hydrogen, or the hydrogen up into where it is, and then I'd have to rotate the nitrogen back a little bit. So this is the conformation that you need for Cope. You need it looking like this. You need it to look like that. For Hoffman, it needs to look like this. It needs to be zigzagged. What else? Bless you.
But all the reactions from the derivative sheet, the test, or just the ones covered?
All the reactions from the derivative sheet, are they on there? I don't know. Let's take a look. So these ones, yeah, when I did this yesterday and said, oh, we know all these, did you immediately run home and figure out what they were? Because my intent was to put these reactions on there on the exam exactly like that. Probably should tell you that. Don't have to. So I would know what the products of those 4 reactions are. The next one, we did this. I showed you that one. We did the mechanism of this one right here, because that was the mechanism that we did. Or maybe I know I did it in the afternoon. And then I didn't do any of these. So I did not do any of those in your class. We had a little extra time in the afternoon, so I did those. So could I ask you any of the ones that we did? Yes. And we could run through these, and I could ask you, like, when you take two equivalents of a Grignard or of an organolithium and react it with an acid chloride, what do you make? Abby? You make a tertiary alcohol. We make a tertiary alcohol. Anything special about that tertiary alcohol? 2 of the groups. 2 of the 3 groups are from the Grignard. Right. So when we did Grignards, that's what we had with an alkyl or with a carboxylic acid chloride. Let me skip ahead, because when we reacted 2 equivalents of Grignard or organolithium compound with an ester, which is next to it, this one, what did I get? So 2 equivalents of organolithium or Grignard with the ester, what did I get? I get the same thing. So I still get a tertiary alcohol with 2 of the 3 groups coming from the Grignard. So those 2 reactions we talked about back in the Grignards chapter. So we get the same product, and the telltale hint here is 2 Grignards. Whenever I'm reacting 2 Grignards, I'm reacting 2 R groups. So I'm going to get a tertiary alcohol in both those cases. Going back, when I add the cuprate to the acid chloride, what functional group did I get? Bless you. That's a little bit more recent. We get a ketone. Where the group that is added, the group that replaces the chloride, came from the cuprate. So cuprates only add 1 R group. How can you remember this? Well, you can just flat out memorize it. I mean, I'm not supposed to say that, but because memorization is bad, right? We're supposed to learn it, right? Then learn it by memorization. But think of it this way. And again, I can only give you my system here. I can't give you I can't create a system for students. And Lord knows I can't mess up their system. I had a research student, that's all she did was yell, you're screwing up my system. Back off, I'm not screwing up your system. But these are all carboxylic acid derivatives. What do we do with carboxylic acid derivatives? We replace that other group with something. That's what they do. That's how they react. So when you have an ester or an acid chloride or an anhydride, particularly the top three, you're replacing that group, the chloride, the carboxylate, you're replacing it with something else. So in these organolithium reagents and these hydride reagents, I'm replacing that other group with an R or an H. The only question is, how many? Well, when I add 2 Grignards, I'm using them both. Almost all the time. With the cuprate, because it's a milder reagent, I'm only adding 1. So I'm adding the ketone. And I think we did the mechanism for that last week. When we do hydride, lithium aluminum hydride has how many H minuses? 4. So that means I can max out the number of hydrogens that get added. So when I take an acid chloride and I react it with lithium aluminum hydride, what do I make?
Primary alcohol.
I make the primary alcohol because I'm maxing out the number of hydrogens that I'm adding. When I add lithium tertiary aluminum hydride, how many hydrogens do I have available? Uno. And so if I add 1 hydrogen, what's that going to do? Replace the chloride, so that what product do I make there? I make the aldehyde. So you can create a system for this based on the reactivity of the Grignard, the cuprate, the aluminum hydride, or the tertiary aluminum hydride. Now, if you go back a couple of weeks, I kind of tried to set that up. So those are all the products of those reactions. So, how about this one? Lithium tritertiary aluminum hydride with an ester. What do you think you will get? Katie?
Just alcohol.
You're just going to get the aldehyde. One hydrogen replacing the OR group. That would have been very disappointing with all that buildup if we don't get that one right. Now, what about the nitriles? I'll leave the nitriles off. I could go through those, but you still have questions. If you don't have any questions, I can certainly go through those, put them on the exam, since that's incentive for asking more questions. Patrick?
Can you go over the mechanism for protecting an aldehyde?
Protecting an aldehyde. So, I think the context of that was, let's say that we had something like this. I had this alkyl halide, and I wanted to add magnesium and carbon dioxide and then H plus H2O to it, because what I want to do is I want to replace the Br with a carboxylic acid. So that's my synthesis that I want to do. The problem is once I make the Grignard's going to attack the carbonyl. So I need to protect the carbonyl first. How do I protect the carbonyl? By making it into a cyclic ketal. So what I would do in this case is I would react this with H plus and ethylene glycol. That's going to convert the ketone into a cyclic ketal. So and you just need to practice that, writing that 5-membered ring, because that's what it's going to look like. Right now, I can go ahead and add my magnesium metal to that. So that's going to make my Grignard. And I'm going to react that Grignard then with CO2. So that's going to make carboxylate because I haven't added any acid yet. Now, remember, acetals and ketals are stable to everything but and acid. They're stable. This cyclic acid, this cyclic ketal, or any ketal, any acetal, is stable to any reagent except acid and water. Because now, after doing a Grignard, what do I normally do? I add acid and water, then H plus H2O step. So when I do my then H plus H2O step, not only is it going to protonate the carboxylic acid, but it's now going to react with the ketal here and convert it all the way back to the ketone. So there's only a few reactions that I can use to protect a ketone. I like this one because it's basic, because I'm doing a Grignard. So it's under basic conditions. I can't protect an aldehyde or a ketone against a reaction that's going to have acid and water. So the acid and the water converts it all the way back. And remember, that's chapter 22, aldehydes and ketones. What did we make? Hydrates. Hemiacetals, hemiketals. Acetals and ketals. We made imines and shift bases. Every one of those is unstable to acid and water. Acid and water will take every one of those compounds all the way back to its original aldehyde or ketone. So that's how we can use it to protect. And you'll see different mechanisms, the different mechanisms I can ask you, because there's like 5 in that chapter alone. Right? So there's the number of mechanisms I could ask you is pretty high. Because I could ask you to make a hydrate or take a hydrate and reverse it. But at this point, what I hope you see is that it's kind of the same steps just over and over again. Forward or backwards. What else? Abby? The cyanohydrins, how to make it? So cyanohydrins, we take an aldehyde or a ketone and we add C triple bond N minus first. So I mean I could ask the question, what happens? And here's the thing, if you look at this and go, I don't remember the product of this reaction, don't panic yet. You might want to move forward and answer stuff that you can answer right off the bat and come back. But if not, go back to the basic principles that we've done. What's going to happen in this step? The nucleophile is going to attack the carbonyl carbon. Okay, what's going to happen next? Well, the oxygen, first of all, is going to try and do what? It's going to try and reform the carbonyl, can it? No. In our case, no. So H is not going to leave, and the C triple bond N isn't going to leave. Although that's not always the case. But in our case, it will be. So since I formed a carbon-carbon bond, it's not going anywhere. So what's it do? Bless you. It just hangs out until I add H+. So now I'm going to add my H+, H2O, and I've now made my cyanohydrin.
And the C triple bond N does. Oh wait, does it go back to a carboxylic acid?
So then what I can do with this, and now we know that this C triple bond N is a nitrile. A nitrile is a carboxylic acid derivative. As a carboxylic acid derivative, if I now react that with H plus H2O, that carboxylic acid derivative undergoes hydrolysis so that I can now convert that C triple bond N into the carboxylic acid. And so now this is, and we'll find this out on Monday, that carbons next to the carbonyl are labeled the alpha carbons, which is exactly the opposite of the way we used alpha and beta in E2s, but that's now called an alpha hydroxy carboxylic acid. Which has a property that it really retains moisture, so that's why it's used in skincare products. I don't know if it's Easter break is a good time to watch a lot of TV, and I forget who Eva Longoria was talking about this stuff you put on your face, and I think that has this in it. It's called hyaluronic acid or something like that. But that's what these products are used for. Before we didn't know anything about carboxylic acid derivatives. And now hope we know anywhere from a little bit to a lot. So carboxylic, the C triple bond N, derivative, hydrolyze it, carboxylic acid. So that was the whole sequence that we did. And the reason I have to use this is because if I tried to use HCN, I would die. Because HCN is a poisonous gas. So instead we have to use cyanide. And then H+. Again, probably not much better, but that's why we use CN- and then add H+ versus HCN.
I know you said on this paper, the carboxylic acid derivative, that we don't need to know the nitriles. Do we need to know the amide one on the very bottom of it?
We will. If I'm going to skip, this is from the last. And if you didn't get the handout from yesterday because you weren't here, I have extra blank ones up here. Plus, the video from yesterday was not from this class. It was from the afternoon because I didn't record the morning. So if you want, those notes are there and you can fill them in. That one, I'll just go ahead and give you what the product is. That gets reduced down to a primary amine. But we'll mop up these guys. We'll mop them up next week and then move on to our condensation reactions. If you look here, I actually did those in the afternoon class. The issue with lithium aluminum hydride plus an amide, lithium aluminum hydride plus an ester. The difference is the ester gets split in half, the amide doesn't. And that's what you have to remember about the lithium aluminum hydride. And the mechanism for this reduction has the aluminum coming in. It's very well laid out in the text, but it's a little different than it wouldn't be something that we could just whip out. So you just have to remember amide, and here's something you could remember. So which one's more stable, amide or ester? What's at the bottom of the list? Amide. So amide's more stable than ester. Ester's more stable than anhydride. Anhydride's more stable than chloride, than acid chloride. That's why the list is the way it is. Amide being most stable doesn't split apart. Ester being less stable does. If you want a better mnemonic, feel free to beat that, because I'm sure you can. And anything that sticks in here for you, use it. So those ones we'll talk about. It'll take about 5 minutes or so. Right. If you have any other questions, shoot me an email. try and come and see me. I will be around. If you can't get to me by 4:30, I will be around this evening, so I'll keep the door open if you want to, or if you want to shoot me an email, or you want to try and see me tomorrow. That's going to be a nightmare, but I am going to be around. If you want the notes, if you want the blank notes from yesterday, you can come up and get them. If you didn't get your homework problems that I handed back last week, you can come up and get those as well. They're probably the other staff. Let's see. Let's see. Aaliyah, Maddie, Melanie, if you're still here. Ashton, Michael, Maddie, other Maddie, Melanie.
Was this greater or for completion?
It was for completion, which is why it should say
Check the answer.
check your answers against the key.
Okay. Thank you.
Okay.